All right, so we want to find domain and range today, locate zeros and y-intercepts, and then also find intervals of increase, decrease, positive, and negative. Okay, so here we go. First, we'll talk about domain and range again and kind of review some different ways we might be asked to find the domain and range. So remembering from yesterday, domain, was that the x values or the y values? Yep, domain is x. And range is the y values. Okay, so something that we didn't mention, or we mentioned a little bit yesterday, but we didn't say this word for it, was the implied domain and range. So the most common domain and range is all real numbers. So that's kind of the implied, unless you see a reason to suspect otherwise. So unless you see something in your graph that shows that it might not be negative to positive infinity or something like that. So the implied range or the implied domain is negative infinity to infinity, and that's the most common. We see that one a lot. And easy ways to tell if it's going to be negative to positive infinity. This happens for domain if on the ends of your functions one arrow goes left and one goes right. So for example, if we see something like this, we have one arrow going off to the right, we have one arrow going off to the left, so our domain would be negative to positive infinity. Same thing happens for range. If one arrow is up and one arrow is down, and there's no gaps. So for example, if we had something like that, we have one arrow pointing up and one arrow pointing down forever. Okay, so that would be your negative to positive infinity range and domain, but there's other possibilities, which is kind of what we touched on yesterday. We talked about a little bit of how to denote these other possibilities, but we only really talked about one or two of these. So I wanted to go over some others that we might see. So yesterday we mainly talked about this case where you've got a parabola or something like that, where the domain might be all reals, but the range would only be values from 1 to infinity, inclusive on the one side. So that's one other possibility. That's the main one that we talked about. But another possibility would be if we see something like this, where we have this open dot and then our function beginning right there. What does the open dot tell us? Are we including or not including that value? Yeah, we're not. Since it's open, Thinking way back to algebra, probably, when we first learned about that with, yeah, line, with the greater than or equal to, less than or equal to, all of that. Yeah, the open dot is not inclusive. So when we go to talk about our domain, the domain is the x values, right? We have only x values starting at 2 here, and then going off to the right. So we would not include 2, and we would go on to infinity. Range is the same idea. We begin at 3, but not including, and go off to infinity. Another option is where we have something called an asymptote. So we might have something that looks like this. Say that's at 2. If your function looks like this, you've got some asymptotes going on. So this is where you're going to have specific values that are excluded from your domain and from your range. We've got an, for our x values, there's one x value that we never quite reach here, and that's 0. So for the domain, we go from negative infinity all the way up to 0, but we don't include 0. But then we include all of the values that are positive past 0. So we would do the whole like union it with 0 to positive infinity, not inclusive on either side. So when you want to exclude a value, remember that's how it goes. You put the value that you want to exclude there next to the set union. And then we do the same thing excluding a value from the range, because we can see that the y values never get up to 2. It gets really, really close to 2, but it never gets there. So we do the same thing excluding 2. Okay. And then the last case I want to show is where you get some kind of funky looking piecewise functions that might look something like this. We'd have, you know, we could have something like that. And maybe that's what our function looks like. In advanced algebra trig, you probably graphed functions in Desmos that looked something like that, where you had to start and stop it at different points. So for our domain here, for our x values, we've got an arrow going to the left. So we know that it's going off to negative infinity. But what's our maximum x value? Since we don't have an arrow on the right. We just notice, okay, as far right as my function goes is right here. It stops. And that's at 3. So my domain stops at 3, but it's inclusive since this is a closed dot. So that would be my domain for this function. We have it going forever to the left, but we have it stopping at 3 on the right. Our range is going to look a little bit different because there's this gap here. So this is how we deal with the gap. So for the range, we know that it's going to go off to positive infinity at some point because we do have an arrow going up, but we don't have an arrow going down. We have a lowest value for our range. We know that we need to include negative 1, 2, 3 in our range. So the way that we include just one number down here for our range is we go -3 to -3 inclusive. That's how we deal with the fact that we've got this one y value of -3 down here. And then it starts up again up here at +2. So we're going to union it with 2. And then we can continue on to infinity. Okay. So those are some other possibilities that we could have for our domain and for our range when we're looking at it graphically. So looking at those 4 examples, are there any questions at this point? Any numbers we're not sure how we got them or why they're there? Yes, it does matter, because this is saying from 2 to infinity. If we put the infinity first and said like infinity to 2, it wouldn't really make sense because you're kind of thinking of it in terms of a number line. You wouldn't have, infinity on the left. It would be negative infinity on the left. So yeah, generally speaking, if you ever find yourself putting infinity comma something, you don't want to do that. Or if you find yourself going something comma negative infinity, you don't want to do that either. Negative infinity is always on the left, positive infinity is always on the right. That's a really good question. I see a lot of people make that mistake. Specifically because they're thinking, oh, it's the infinity is up here on the left side of the function, but when you're writing it like this, it's on the right. Any other questions or any numbers that don't quite make sense on here? Okay. All right. So then we also want to be able to find domain specifically if we're given just the written out function equation versus the graph. So we're going to do that as well on another piece of paper. Okay. So given equation, find domain. Okay, and you usually will be able to have graphing available so that you can, visually see the domain, but finding it from an equation is just kind of interesting, and shouldn't be too tough to do. If I have something like f of x equals 1 over x, you start with your implied domain. You think, okay, this could be negative to positive infinity, but are there any values that I couldn't plug in for x here? Are there any values that I can't divide by? There we go, 0. Yeah, I can't divide by 0, right? So if I plug in 0 for x, like if you did that in a calculator, it would be like error. Can't do that. So whenever you're looking for a domain, especially when you have something like this, an inverse function, or not inverse function, but yeah, reciprocal function, then you're looking for places that x can't go, basically. So what this one actually ends up looking like, if you were to graph it on Desmos, is it ends up looking something like this, where you've got this asymptote here, that x never quite gets to 0, and then y also never quite gets to 0. But yeah, anyway, so recognizing this, you can just put that your domain is the one where you exclude 0. Because that's how we exclude values. So likewise, if I had something like f of x equals 1 over x minus 7, it's the same idea. What value of x is going to make my denominator 0? Yeah, 7. So 7 is the value that we have to exclude. So in our domain, we'd end up with negative infinity to 7, unioned with 7 to infinity. Or if we had something like this, stepping it up a level. 2 over x plus 3 over x squared plus x minus 2. This is where we kind of drag out the factoring again. What's one value that x can't be? 0. Yeah, that's the obvious one, right? We've got 2 over x. That's the same idea as 1 over x. So we know x can't be 0. Then we got to factor this thing. So we get x plus 2 times x minus 1. Remembering our factoring. Because remember, we would look for things that multiply to get -2 and add to get 1. For the 1 in front of the x there. And it just so happens that it's 2 and -1. So then our other values that x could not be would be -2 and +1. So then we go, okay, well, then we have to write our set notation, or our interval notation, well, excluding each of these 3 values. So this domain is going to look a little bit ugly. We're going to start at -infinity, and then you just pick the smallest one. The smallest one is -2. Then we union that with -2, but not all the way up to infinity, because we still have to exclude 2 more values. We have to exclude 0, since that's the next smallest. And then we have to exclude 1, because that is the last one that we have to exclude. And then we can go from 1 to infinity. Okay. So that's a bit of an extreme example of excluding specific values. There would be asymptotes at each of those, or occasionally there'll be one where you get something like that, but there's a place that just has a hole in the function. But anyway, that would be our domain for something like that. All right, we'll do one more because there is one more type of question like this. It won't look quite as ugly as this, but where you'll see a change to the domain. It'll only exist for a specific set of values. That's if we have f of x equals something like square root of 3 minus x squared. Okay. So thinking about real numbers here, are there values that cannot go underneath a square root? Is there anything that if I square root it, it's going to come up with either an error in the calculator or an imaginary? Yeah. Nice, Carson. A negative number. Yeah, you can't stick negatives under a square root unless you want to deal with complex numbers, which we're not. So if I were to graph this in Desmos, it's going to graph me a half a circle, or a half circle. Let's see. Yep, that's what it would come up with. Especially because of the way that I've written it. So our domain is going to look like basically all the values that would make, or whatever is under here, 0 or greater. So if I go, okay, 0 equals 3 minus x squared, and then I subtract 3 from both sides, we get -3 equals negative x squared. And then we get 3 equals x squared. And you get plus or minus √3 for x. And then the easiest way to check and see if you're going to have your domain be the values that are inside this range, -√3 to +√3, or outside the range, is to plug in something that's inside the range. So if I had -√3 to √3, if I plug in something that's inside this range into here and it works, then that means that this will be my correct domain. If I plug in something that's outside that range of values in here and it works, then it means that it would be the everything except for this being my domain. So since 0 is inside this range, or this range of values, not the range, not the y values, since 0 is inside this set of numbers, if I plug in 0 here, we get the square root of 3 minus 0, which is something that we can do. So that tells me that my domain is going to be the values that are inside here. that makes sense. But yeah, so that's kind of the other possibility that we could see in addition to these. These are the ones that will probably be asked the most often to find a domain based on looking at the function. But then again, also with pretty much all of these, you'll be able to plug it into a graphing calculator and be able to kind of visually inspect it as well and get the case that's up here, where you can just take a look at the graph and figure out what values you might need to exclude. Okay, so that's our domain and range stuff for today. Now we're going to move to intercepts and zeros and stuff like that. So for Y-intercepts, well, the Y-intercept is whenever it touches the Y-axis, right? So when your function's touching the Y-axis, that means X is 0. So all you have to do to find the Y-intercept is just plug in 0 for X. So for example, if I've got something like this, not Y, f of x equals x cubed plus 1. Well, to find the Y-intercept, you just find f of 0. So the point 0, 1 would be your Y-intercept. Okay. So then that way is simple enough usually. Zeros or X-intercepts can sometimes be trickier. If you're using a graphing calculator like Desmos or even your TI calculators, you can pretty much just click on it. With the TI calculators, you have to do a separate function. You have to hit second calc. And I'll go through that in a moment. But in Desmos, you can just click on it. Or if you're solving for it algebraically, that's also an option. And sometimes in college, you're expected to do things algebraically that you might otherwise have a calculator for. So we'll do that for an example. I'll show it algebraically and I'll show it with a calculator. So if we have the function 2x cubed, or not plus, minus x squared minus 3x. To find the zeros, the x-intercepts, you just set the function equal to 0 and solve from there. But this is where we're going to have to bring out our factoring skills. Who's excited to factor? Where's that false enthusiasm? All right. So factoring, first we got to take out the greatest common factor. Shake off the cobwebs. So first, the GCF, they all have an x in them. So first we factor out an x. Then we got to factor this bad boy. So 2 times -3 is -6. We're looking for things that multiply to -6 and add to give us -1, which just so happens to be -3 and 2. Those multiply to -6, they add to -1. So what we want to do is rewrite it. 2x squared minus 3x plus 2x minus 3. We still got our x hanging out in front. Then remember, we split it down the middle, and we take out the greatest common factor from each of these. So this one has an x. So we go x times 2x minus 3. This one, the greatest common factor is just 1. 1 times 2x minus 3. And now they both have this 2x minus 3 in common. So now we have x plus 1 times 2x minus 3 times x. And this whole thing was originally equal to 0. So now we just set each of these pieces individually equal to 0. So x equals 0, x plus 1 equals 0, 2x minus 3 equals 0. So our x-intercepts would be at x equals 0, -1, and +3/2. So if we were calculating our zeros algebraically, there we go. Or you can just do it on your calculator. So looking at, if you have a TI graphing calculator, I'll show it this way. In Desmos, you can just type in the function and then click where it crosses the x-axis. This way is a little bit more complicated, but it's something good to know, especially if you're going to take AP Calculus. So here we go. We type y equals, or we hit the y equals button. And then we type to the variable button x to the 3rd power minus x squared minus 3x. So we would type that. And then before you graph things, usually you want to check your window. I like to have the x minimum be like -10, +10, if I don't know exactly where my function is going to be. And then the y minimum and maximum be the same thing. And the scale be 100, just in case, so that it's an easy to see window. And then you can kind of adjust from there once you hit the graph button. But that usually graphs it pretty nicely. Then if you want to calculate the zeros, you have to hit second and then the trace button, because that has that calc above it. And then you can say, well, I want to calculate the zeros. So for my first 0, you want to choose like a, they call it a left bound. And here, I'll zoom in. So you just put it so that it's to the left of your first 0, and you hit enter. And then you choose a value that's to the right of your first 0, and you hit enter. And then you hit enter one more time, and it tells you where the 0 is located. And you can do that for each of your zeros. So you can go, okay, and then second calc again, 0. And this time I'm going to do my second one. So I'm going to go, okay, this is to the left of my second one. This is to the right of my second one. Hit enter again, and it finds your 0. And then for the last one, you go second calc again, 0. You pick something to the left of your first 0, something to the right of your first, or your third 0, I mean, and then you hit enter one more time, and it tells you where it is. So that's how you would do it if you're using a TI calculator. But yeah, and then you also have the Desmos available to you. Okay, so there's our zeros. There's our intercepts review. Last thing we want to talk about is briefly here, increasing, decreasing, positive, and negative. First, increasing / decreasing. These are how I like to abbreviate it. Increase, decrease. If I have a function that looks like this, we'll say that this value is 3, that this value is -1. Okay, So my function is increasing whenever it's going uphill from left to right. So it's increasing here all the way until it gets to the top of that hill. And then it's decreasing. It's decreasing in pink. And it decreases until it gets to the bottom. And then it increases forever. So my intervals of increase would be -infinity to 1, or sorry, -1, because we're picking the x values on which it's increasing. And then it would be increasing again from 3 to +infinity. Okay. And we don't include the -1 or the 3 in our intervals because at that particular point, it's not increasing nor decreasing. It's just flat. So then it's decreasing from -1 to 3. So that's increase and decrease, uphill versus downhill. Then we have intervals of positive and negative, which we will do similarly. And we'll say that this is when x is -4, -1, and +4. Okay, so anything that's below the x-axis or y-axis, I mean, remember, is negative. Anything that's above the y-axis is positive. So here we go. We start out negative. We are negative from -infinity to -4 first. Then we become positive from -4 to -1. Then we dip back below the y-axis from -1 to +4. But then we go back above the y-axis off to infinity and beyond. So those would be our intervals of positive and negative. Okay. So today we have talked about domain and range, a lot of things. Y-intercept, X-intercept, increasing, decreasing, positive, and negative. So looking at all of that, are there any questions that come to mind at the moment? Any numbers throughout that we're not sure where they came from? Or do we just need to kind of digest this and work on trying a bit on our own? Okay. So today's assignment is going to be a Desmos activity. And it's going to kind of walk us through some graph analysis here. So I'll assign it, and you guys can pull it up, and then we'll talk a little bit. Okay. So jump over to Classroom and click on that 1A graph analysis that just popped up. Enter your name to begin, and click Go. So then just kind of, we're going to be going through each of the slides. There are, I think, 19 slides. Not all of them are very long. Like this one, you can just tell me some general things that you would tell me about this graph. What do we notice? What's with the endpoints? Are there any places where it crosses the x-axis or the y-axis? Tell me what you know about the graph, and then submit it and move on. If you have questions at any point about what something is asking, feel free to hop back on and I can help you out with that. Class today is over at 1:45, so at 1:40 we will all come back together and kind of debrief here. So your assignment for today is to go through these slides best you can. Ask me questions if you have them, and also remember to finish up what we did yesterday in Khan Academy, but start with this. Okay, you are free to go get started. You can stay on here if you would like, or you can take off.